All right. So, the last piece of content for the whole course is a lecture on design software complexity. This is the last lecture in the course, also the last lecture in design. And what we're really talking about is how do we understand software complexity? It's an interesting little topic. Again, it won't be too lengthy or complicated, but it has some points that are very, very worth understanding. Firstly, why we're talking about this is we need a material way to be able to understand and have conversations about how complex software is. It's interesting when you think about it, right? Like if you say to someone, oh, yeah, your software is complex. They go, okay, yeah, sure. And then you go, how complex is it? And they're like, I don't know, kinda, super. Like, how do you talk about it? You know, we have ways of talking about things in reality. You know, someone says, I'm tired. How tired are you? It's like, oh, you know, really tired. I had 3 hours of sleep. I had 4 hours of sleep. You know, I can't think straight. I'm struggling to keep my eyes open. We have ways to describe it. We will benefit as software engineers if we also have ways to talk about how complex our code is. So we're firstly going to talk about a bit of a qualitative description of complexity, and then we're going to talk a bit more about a quantitative description of complexity. So firstly, what is software complexity? It's an interesting question. How do we know if software is complex? Like if you write software, how do you, and someone said, is this complex? You go, I don't know, maybe. Haven't thought about it. So we have to answer that question first. And one great way to reference this is by dividing software complexity into two categories. The first category we can divide it into is called essential, and the second category is called accidental. The great thing about these two categories is that they actually make quite a lot of sense when you really spend some time with it. Essential complexity is complexity that is inherent to the problem. It's complexity that you cannot remove. You know, like if someone said, oh, wow, the Sydney transport system's so complicated because you have buses and ferries and trains and light rails and stuff, you would consider that essential complexity. It's complexity you can't remove. You can't just go replace every ferry with a bus. Buses don't float. You can't go and replace every train with a bus. Do you know how many buses you need to fill one full train? I don't, but I think it's about 200. It's a lot. It's a lot of buses. And you think about Sydney in peak hour, they're moving like, say, 2,000 people a train every 3 or 4 minutes. So you're going to now what? Have like, call it 100, 200 buses every 3 or 4 minutes. It's like 30 buses a minute. That's like loading one bus every 2 seconds. You know what I mean? Like you can't avoid it. It's a bit of a dramatic rant about load capacities in Sydney. So we consider that type of complexity essential. Then we have accidental complexity, and this is complexity that you could, in theory, remove. So if someone said, oh, you know what's so confusing is like all this pricing stuff, like there's like different zones and different distances, and then there's off-peak charges with Sydney Transport, and then there's weekend discounts, and then there's transfer benefits, and then like it kind of goes on for a while. That's complexity that doesn't have to be added, right? If you go to, say, New York City subway, they have a very simple thing, which is every time you tap on, they charge you, I don't know the exact amount, it's like $3 or something. Every time you tap on, $3. It doesn't matter if you go 1 stop, 10 stops, and they cap it out at the end of the week. They say you it's like 12 trips a week or something like that. Full stop. Really simple to understand. So that's an example of like when you look at the complexity of Sydney's transport system. I'm not saying that that's bad complexity, to be clear, but it's certainly it's not essential complexity. You could simplify that if you want to. Where this whole topic, though, obviously gets into a really gray area is that, like, as software engineers, we're writing software that might be complex, and then someone's like, wow, your code is so complicated, and you say, yeah, it's not accidental complexity, it's essential because the state government says these are the rules about all the transfers and stuff. So there's no universality to it either, because like to you writing the code, maybe while someone else optionally added a requirement, that requirement, once it's on your plate as an engineer, now becomes essential. You know, so that's an important thing to think about, because what we're talking about is software, and when it's you write software, the question is, could you, with more time, energy, intellect, guidance, review, simplify the complexity of your code, or is it just how it is? And if you can't, it's essential. If you can, it's accidental. That's the crux of it. Yeah, obviously, and yeah, this is pretty much what I've just talked about, so we don't need to go into too much depth there. Okay, lots of fun questions that come out of that. Questions like, is there a concrete process for distinguishing it? Is there a way we could identify accidental or essential complexity without relying on human judgment? How much complexity in software that we all write these days is accidental? And to what extent can we automatically remove these things in the future? These are all interesting questions that we could ask ourselves. At the end of the day, and I think I mentioned this in an earlier lecture, one of the funniest things that I think is true about software is, again, just how early we are. We've only been programming for like 60 years. So many things we do as people, we've been doing for a very, very long time. So in a lot of ways, we still haven't really figured out a lot of stuff. We still haven't really figured out if, we can just write code that is not complex in the future. So something to definitely kind of keep floating in the back of your head. So that was the qualitative element, essential and accidental. Now, when we get to the more quantitative part, we have to ask ourselves, is there any way possible that we can measure the complexity of software and reduce it to a number, right? That's what quantitative is. Can we turn it into numbers? And there's a few ideas here. The first two are a little bit more qualitative, but the third one is the quantitative one. So let's quickly tackle the last two qualitative points. The first one is coupling. Coupling is a measure of how closely connected different software components are. Basically, and let me just jump ahead. Cohesion is the topic about the degree to which similar objects are together, similar things in the code are together. What we want from our code is we want to have high cohesion and low coupling. Low coupling means things that are different stay away from each other, and high cohesion means things that are similar stay close together. It's a little bit of a funny way to think about it. But what I mean by that is, like, if you have a piece of software, like say, my company, we have a piece of software, and there's parts of that software that are concerned with dealing with financial transactions. And then there's parts of the software that are concerned with dealing with the integrity of those financial transactions, like auditing or checking them, right? And it's like, because those two things are so closely related, you'd hope that they're near each other in code. You'd hope that they're in the same file, they're in the same folder, that they use the same names. And that's called cohesion, when similar things, if they belong together. Because if you have a module where lots of the stuff in there all is connected really tightly, you're like, cool, that makes sense. We have like a place and everything there is related. Similarly, we have the stuff that deals with transactions, like money coming in, money coming out. And then over here, we might have something like an animation for a little login screen that has nothing to do with financial transactions. So you'd hope that those two pieces of software are quite far apart. It's nearly kind of overdone in its explanation, which can make it sound more complicated than it is, but it's really not a lot more than common sense. Saying similar things stay together, different things stay apart. And you know why? Because it makes software easier to read. It makes software less complex. Because in general, software becomes complex when you have a bunch of stuff together that shouldn't be together. And when you have a bunch of stuff that relies on each other or that a developer needs to see goes together, they're like way over, on two ends of things. But in terms of the numeric part, which is the interesting one, there's this topic called cyclomatic complexity. Cyclomatic complexity is a measure of the branching complexity of functions. This is an interesting topic because in a previous lecture, we talked about code coverage. And we talked about one interesting thing about code coverage is that in this course, we measure code coverage by the number of lines of code that are checked by tests. And then what we talked about was that one great way to understand code better is to look at branch coverage, because branch coverage looks at how many different, possibilities there are with if, else, and while statements and things like that. And the reason we said the branch coverage is more interesting is because a lot of bugs in code tend to happen every time a decision is made. Every time an if statement has to decide whether to enter or not, every time a for loop has to decide whether to enter or not, they are a massive magnet for bugs. And therefore, if they're a magnet for bugs, it's because there's complexity associated with that conditionality. So branching, or if, else, while state for loops, are fairly inherently complex. Cyclomatic complexity is simply looking at code and reducing the amount of branching to a number. And the bigger that number is, the more branching there is, the more complex the code is. So to compute the cyclomatic complexity, because the cyclomatic complexity is like an official measure, you take a section of code and you can essentially reduce that code to a graph, and you say that the cyclomatic complexity of that piece of code is the number of edges in that graph minus the number of nodes in that graph plus 2. Plus 2. So random, isn't it? But let's look at some examples together. So firstly, take this piece of code. This is where you kind of just have to stop and really think about code for a sec, because what you see here is that function foo, if A, go B, otherwise go C, and then finish the code. Now, I don't want you to get too caught up on the A's and the B's in the code and trying to link that to the A, B, C, D's in the diagram. But what you can see here is if you were to try and represent how this code works visually, you would see that we're always going to enter the program here with A. Then we are going to decide whether we enter the if statement or we enter the else statement. And then at the end of that, we're always going to finish at the same point. No matter whether we enter or don't enter the if statement, we still finish between lines 6 and 7. So the code, very intuitively, starts here, goes one or two ways, and ends up at the same point at the end. When we represent that as a graph like that, we can count the nodes, 4 nodes. We can count the edges, 4 edges. And then we can add 2, which says 2. Now the cyclomatic complexity is essentially then saying, how many possibilities are there through this code? And we say there's 2. There's only 2 ways this can go. That way, left or right. If we look at a more complicated example, and don't worry about the diagram for a second, you can kind of reason with it and say, okay, well, we got to enter foo, and then we have a point there with A. We can either split off to the left or we split off to the right. And if we split off to the left, we're then just going to go straight to the end. And if we split off to the right, we then are going to either go into the if statement or skip it. And then we're still going to go to the end. So then you start to try and draw it out and you say, okay, well, we're always going to have to hit that A point. Again, you could use numbers, doesn't really matter. I hit the if A, okay, and if it's true, I go into B, otherwise I go into C. You know, C is like this whole section here. All right, and if I go to B, well, once that's done, I'm just going to go straight to E, which is the end of my program. But if I've come into the else statement here, I then have a choice as to whether, like, if C is true, then I'm going to go to D, and if C is false, I'm just going to go to the end of the program. Okay, well, and once I hit D anyway, there's no more decisions to make. I'm just going to go to the end of the program too. So what we then see is that when we draw this out as a graph and we sum up the nodes A, B, C, D, E, we have 6 nodes, 6 edges, 1, 2, 3, 4, 5, 6, plus 2, so the cyclomatic complexity is 3. You'll notice one commonality about all of these is that every single graph should have an input node and an output node, and everything should start from one point and branch out, and then everything comes back to one node at the end. But 3 makes sense here because there's 3 possibilities through the code. I either go through the if statement, I go through the else statement, if statement, I go through the else statement, skip the if statement. So it's just a good way, again, to talk about possibilities, because, you know, the more permutations you have through your code, the more nightmarish it is in terms of the potential introduction of bugs. Here's another interesting piece of code. We have a while loop. Now, again, forget about the diagram for a second. Focus on the code. Function foo. What happens here? We have a while loop. Okay. We enter the while loop, and one or two things can happen. Sorry, we don't enter the while loop. We approach the while loop, and one or two things could happen. Either A is true, and we enter the while loop, or it's not true, and we skip it. So if A is not true, we go straight to the end C. If A is true, we enter the while loop. And what happens when we enter the while loop and we get to B? Well, we simply have to start again. Because once you get to the end of the while loop, what do? You approach it again, back to the start. So that's what that diagram looks like. And when you draw it out with the formula, you get a situation of A, B, and C where, you know, there's 2 possibilities through the program, which is basically either you go into the while loop or you don't. Now you might be thinking, isn't there theoretically infinite possibilities? Because like you could either skip the while loop, you could enter it once, you could enter it twice, you could enter it 3 times, you could go around 4 times, 5 times, 6 times. Yes, but what we're tracking with cyclomatic complexity is not how many literal movements through the code you do. It's like how many different decision points are there, because this is still one decision point. Even though you might get prompted with that decision a million times, it's still the same question being asked. And that's really important. Now, one interesting thing about cyclomatic complexity, just to really make this point super clear, is if we take this for a second, make it a little bit bigger. Let me make the background black for you. So, no, it's the wrong shade of black. Ah, my OCD kicking in. Ugh. How do I make the brush thicker? Oh, there. We're going to solve this quickly. Oh. So, oop. Okay. Anyway, I'm not a very good drawer. I'll just do a little bit, make myself feel better. Okay, well, that was silly. So let's imagine that we have this diagram, which used to look ugly, but after I've touched it, it looks uglier. And we say, well, we know the cyclomatic complexity of that is 3. We've seen that before, because over here, we say number of edges minus nodes plus 2 equals 3. 2. Sorry. Now, the interesting question, again, comes at, for me, if you think about this code example, right? Maybe I can copy and paste that in to the thingy. Think about this code example for a second. What if I drew this differently? What if instead of... all right, sure. No. Anyway. What if instead of drawing it like this, I instead tried to use line numbers? And I said, okay, we're always going to start at line 1. Make that really big. We're always going to start at line 1. All right. Now what happens is we're going to go to line 2. Cool. From line 2, we have one of 2 options, which is we're either going to go into line 3, or we're going to jump straight to line 4. And then from line 4, we're naturally going to always go to line 5. And then from line 5, we're always going to go to line 6. And then we start drawing some lines between it. I think my lines are a little bit big at the moment. Like this. 1 to 2. We know that 2 can go to 3. We also know once 3 is done, it has to go back to line 2. And at some point, 2 jumps straight to 4 once you don't enter the while loop. And then this comes down here. And then this comes down here, like that. Now, this is a wildly different representation of the same thing. But the cool thing about the formula is if you draw the graph in any way that's valid, you get the exact same answer. So for instance here, if I was to just write this out, how many edges do we have? 1, 2, 3, 4, 5, 6. 6 edges minus how many nodes do I have? Let's count them out. 1, 2, 3, 4, 5, 6 plus 2 equals 2. Same number, you know? So that's one really cool thing about cyclomatic complexity and why you shouldn't get caught up on the drawing element of it, because as long as you draw it in a way that is true, anyway, that's true, it's fine. And that's also why it actually makes a lot of sense, because if you draw unnecessary lines, like let's imagine this piece of code had like, you know, C, D, E, F, G, or just one after another. If you just draw linear things, they all cancel each other out. Because if you think about the formula, it's E minus N plus 2. So if every time you add a node, you only add one edge, you kind of don't change the formula. So it's a really cute little thing, I think. Here's a more complicated example for you. A function that converts days to years. So you give it a certain number of days since, you know, 1970, January 1st, 1970, and it tells you what year it is. And you can see if you think about this function for a bit, okay, you enter it, we kind of ignore these one-liners, and then you hit a while loop. Okay, well again, maybe let's draw that out together. And I could really draw this one in a great level of detail if you'd like to. Maybe we'll do that. Yeah, sure. Okay. Maybe let me make it black. Black was nice and soothing on my eyes. All right, so what we say is we say, okay, well, I'm going to enter again on line 1. Okay, then from line 1, I'm going to go straight to line 2. From line 2, I'm going to go straight to line 4. From line 4 now, I'm either going to go to line 5, enter the loop, or I'm going to go straight down to line 14, I guess. Right, skip the whole while loop. Now, once I enter the while loop from line 5, I can either go to line 6 if I enter it, or I can go straight to line 10. So from here, it's either line 6 or it's line 10. Cool. Let me start drawing some lines in just so we don't forget. 1, 2, 4, 14, 5, 10, 6. From line 6, I can either go straight to... I can either go into 7. Silly how it does that. Or I can skip that if statement here and go straight to line 9. And obviously, if I go from line 7, I'm going to go to line 8 as well. And then after line 8 is done, what happens is I just end up going straight to line 9 anyway. So either I go from line 6 to 9, or I go from line 6 to 7, which goes to 8, which ends up back at 9 anyway. And then from line 9, because I don't go in the else statement, I end up going right to 14. And if I did end up going straight to line 10 with the else statement, then I'll naturally go 11, 12, and 14 anyway. Now, I could put an 11 and 12 here, but I could just go straight back here as well. I'll just go and add some arrows on for you. There we go. So now I could look at a diagram like that, and assuming I haven't made a mistake, and I do make mistakes, trust you me, I could add it up and say, well, 1, 2, 3, 4, 5, 6, 7, 8, 9. No, I didn't count right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges minus how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes plus 2 equals 4. What's the answer? 4. Notice this diagram was different. It mostly didn't include a bunch of redundant things. Because again, anytime you have a situation like this, where you have one line connecting to another, you don't need it. You could cut that out. You could cut this out here. Everything else you'd kind of keep. But if you actually just thought about this diagram where you cut those two things out, right, and you just kind of had that, you would end up seeing that it produces basically the exact same thing. So lots and lots of different ways to draw it. And then last one here, let's just think about this one quickly. See if we can just look at the diagram. You start from the top, and then you have one or two choices. You either enter the while loop here, or you totally skip it and go to the end. Okay. Once you enter the while loop here, you have two choices, which is you either go in the if or the else. And regardless of whether you go in the if or the else, you still end up on line 10 at the bottom. And once you get to line 10, you have to go back to the start of the while loop anyway. So this diagram makes sense too. And you could draw it in a more verbose way, but you couldn't draw it less than this. The diagram physically has to have this much minimum content in it, just because, you know, if you drew any less, you wouldn't be capturing the code. But in that case, you see the same thing. 7 edges, 6 nodes, plus 2, 3 branching factors, which makes sense because the code, you can either, well, it's not really 3 branching factors. It's like, yeah, it's like you enter, you either enter or not, right? So there's 2 options, but then one of the options has another 2 options in it. So there's kind of like that way, that way, that way, or that way, that way. Just again, a numeric representation essentially of possibilities, conditional possibilities. So this is a great way to measure complexity. And if we wanted to, it's not something we do because 1531 is probably already quite thick in many ways. But if we wanted to, we could do some checks where we actually say to you, we want you to focus on keeping your functions nice and simple. And if we see any functions you've written that have a cyclomatic complexity of more than 6, more than 7, more than 8, then we would take marks off you, just like the linter, just like TSC, just like coverage. So you're starting to see there are lots of tools that we use as software engineers to keep our code stable, whether it's linting, TSC, or in this case, basically a quantitative complexity checker. That's what we're doing right here. One of the drawbacks of this approach, of course, is that it does make a very strong assumption that non-branching statements have no complexity, which isn't always true. Sometimes you can get code that's just like really long. Like in this case, a function that has no if and else statements in it, no while and for loops, but is a million lines long, would be considered to have a cyclomatic complexity of 2, 1, right? 1 edge, 2 nodes, -1 plus 2 is 1. So that would be weird because a million line function does not have a trivial complexity. It has a real complexity. So that's one drawback of the approach. The second drawback of the approach is that keeping the cyclomatic complexity low may encourage splitting up functions in cases where it's not desirable. Sometimes, like anything we've talked about in this course, it can be better to keep things together, even if they're a little bit more complex. And that's why, as engineers, we need to keep upskilling so that we have good judgment when it comes to that stuff. Naturally, we can calculate this too. I've mentioned that before. So automatic calculation is possible because it's a fairly deterministic thing. We could make a project for you where like your job could literally be to take in JavaScript code and try and see if you could output the complexity of it by basically looking for while loops, for loops, and stuff. It'd be a fun little assignment, honestly. But we don't have time, but it would be fun. There's some further reading on the topic, but besides that, it's pretty much just a Q&A again. Does anyone have any questions about cyclomatic complexity or just complexity in general before we wrap up this particular lecture? I'll give everyone about like 30, 60 seconds. Can you hear the birds? I don't know if you can hear them when they make sounds. Yeah, looks like you can. I have a bunch of birds on my windowsill. They're so cute. Nearly there. All right, sounds good. Thank you very much.